Okay, imagine that we have a dipole and we want to find the electrical field produced by the dipole just only on the direction where it's joining the negative charge with the positive charge in this direction. Let's say that this is the x direction. So we want to find the electrical field at this point that is near the positive charge and farther from the negative charge. So you know, as we have discussed, that the electrical field should go in this direction. Or maybe we want to go to find the electrical field in this in this point P. Now the electrical field produced by the negative charge will be like this, and for the positive charge will be like this, and the total electrical field should be to the right, because this will be bigger than this one produced by the positive charge because it's farther. So this is the electrical field. If you represent the electrical field, you will find that if here is the negative charge, and here you put the positive charge, this distance is d divided by 2. This distance is d divided by 2. The electrical field is positive, you see, it's pointing to the right. It's positive, and when you approach to the charge, the electrical field is very, very big and going to the right. While on the other side, the electrical field is also going to the right. The electrical field here is going to the right in this area, in this section. Is going to the right, so the electrical field is positive, and as you go further, the electrical field decrease. So what we are going to see is an approximation that say that the electrical field from points, the electrical field E sub x, this is the electric dipole P is here, okay, it's in this direction. The is Q by D. Okay, the electrical dipole is the charge, the positive charge, by the vector d, this vector from the negative charge to the positive charge, this vector d. So P will be a vector in this direction, maybe like this. Okay, if Q is 2, will be like this. If Q is 2, it will be 2 times d. Okay, so the electrical field, what we are going to see is that for points that are very, very far, even the charge is 0, the total charge with the positive and the negative charge is 0, the electrical field at a point x from the 0, from the origin, this is the origin, x, at this point x, the electrical field will be approximately P, the vector P, divided by x cubed. X cubed, no x squared, x cubed. Well, with the k, of course. K, P, divided by x cubed. So the electrical field will go to 0, will be a small quantity, but the approximation that we are going to use will show that this is the electrical field. So let's go to approximate. In the middle, this is the electrical field in the middle. If you are at this point, you are much more near of the negative charge than what the positive charge is. So if you are here at this position, the negative charge will be, the electrical field produced by the negative will be very intense, so it will go to the left, while the positive charge, the electrical field, both of them, the negative, both of them will go to the left, so the electrical field will be negative. At this point in the middle, the electrical field produced by the negative charge will go. You see, I think I made a mistake in this picture. This picture is not like this, because at the zero, the electrical field is not 0. At the 0, the electrical field is, this is the negative charge, this is the positive charge, you are just in the middle. The negative charge will produce an electrical field in this direction, and the positive charge will produce an electrical field in this direction, so the electrical field will be to the left, so it will be negative, but it will have some value. It will not have this value, so the electrical field should go like this. Sorry. So it's not going like this, not going like this. When you are near the negative charge, the electrical field is very, very negative. When you are positive and very near that a point like this, the positive charge will produce an electrical field to the right, to the left, and the negative charge will produce an electrical field to the left also. So it will be negative electrical field. So it will be like this curve. The electrical field, as you moving, the electrical field decrease, arrive to a point here, and later on, the electrical field decrease. And when it goes very, very near the point, the electrical field produced will be very big, produced by the positive charge, will be very big, but back to the left. So this is the electrical field here, and this is the electrical field outside. There is you can see that 1 over r squared tends to infinity when r tends to 0. So this is what is happening here, okay? So let's go to see the approximation. It's like this. We want to find the electrical field produced by a dipole. This is the dipole. This is the origin. This is the point x. It means here, this distance from 0 to x, okay? This is the distance x. So the electrical field produced by this system, by this dipole of the point x, is the electrical field produced by the positive charge plus the electrical field produced by the negative charge. But the electrical field produced by the positive charge is kq positive divided by the distance from the charge to the point of observation. The distance from the charge to the point of observation is x minus d divided by 2. In the direction of r, in this direction, from the source to the point of observation. So plus the electrical field produced by the negative charge, but the electrical field produced by the negative charge will be k, but q negative, that will be negative, this value will be negative in the vector unitary r in the direction of r from the source to the point of observation, but of course this electrical field will go in the negative direction because the q negative will make the electrical field to go in the negative direction. If you take the magnitude of, if you play like this, the electrical field will be k q positive, and because q negative is equal to minus q positive, I have put the q positive here and minus here. Okay, so you have this. So using what I have shown you in the previous video about how to approximate these fractions, when I have used this approximation 1 plus x to the m. In the case that x is very small compared to the 1, so this number is very small compared to the 1, this is equivalent to 1 plus mx. If you use this approximation here, you will find the algebra is down here, and the algebra will take you directly, if you see carefully what I did that I have done before, same thing, please do it by yourself, and you take the limit when x tends to infinity, you will see that the electrical field when x tends to infinity is the result that I told you. So if you consider a bad approximation, you may think that at x infinity you see a total charge 0, and you may think that the electrical field is 0. It is true that a very far a very far distance, the electrical field will go to zero, because the total charge that you are watching is zero. It's one positive charge with one negative charge, but the positive charge is making some electrical field that is not cancelled exactly by the negative charge. So this is the approximation. This is a very, very useful result to calculate electrical dipole interaction between two dipoles. Okay, two dipoles P1 and P2 interact. How they interact? P1 create an electrical field. Oh, P1 minus positive create an electrical field. The electrical field that produced by the first dipole is acting on the second dipole. This electrical field, what it will do? It will rotate the molecule. It will rotate the dipole. Oh, interesting. And what will be the electrical field that you can consider for long distance? Well, you may think if they are in the same direction, if the dipole 1 and dipole 2 is in the same direction, minus positive, and the other one is minus positive, you may think that the electrical field produced in the center is of the order of Kp divided by xq. So in this orientation, you don't produce any torque. But if the dipole was here, the electrical field produced by the dipole 1 will produce a torque that will tend to align all the molecules in the same direction with the same P. This is what is happening. Also, of course, the temperature will try to disorder everything and will try to create chaos and produce motion in every direction. But the electrical field interaction in between dipoles will try to maintain all the dipoles aligned one with the other. Okay, let me see. Here, I think that's all.